Hello, everyone. My name is Vicente Amado Olivo, and I'm a first-year graduate student at Michigan State University. I'm presenting my work on an automated analysis of tracking facility usage in papers for the Space Telescope Science Institute. So the Deep Thought team at MSU is working on using AI to assist astronomers in handling the increasing sea of publications. We aim to do this by creating tools that implement natural language processing techniques, which is the interaction between language and computers. Being a graduate student in the Computational Mathematics, Science, and Engineering department at Michigan State University gives me the special opportunity to be a member of an interdisciplinary astronomy research group. There's a symbiosis between the astronomy and natural language processing teams. The astronomers in the group can give me direct feedback on what are the needs of the community, and their domain knowledge assists in verifying if the outcomes of the research are sensible, while I can provide them tools that assist in handling the large and complex data set that are astronomy publications. Our team consists of a first-year data science undergraduate student at MSU named Bea, myself, and our advisor, Wolfgang Kersendorf. So first, I wanted to look at the landscape of publication astronomy. Here on the left, we can see the number of papers published per year on arXiv from 1992 to 2019, and currently there are 16,000 papers published per year. On the right, we can then see that this is exponentially growing the astronomy literature. So it has become an impossible task for any one scientist to read all these papers and keep track of the information in these papers, like who is working on what and what questions have already been answered. Astronomy publications are complex data structures, and as the output of these publications continues to increase, it becomes a big data problem. Our team is working on using natural language processing, NLP, for various projects, such as the classification of papers and others that I'll touch on later. In a preliminary study by me, we found that during the same time frame, we can see how many new authors have published an astronomy publication per year. This is important to see that not only is the rate of publications increasing, but the rate of new astronomers entering the field is increasing. This is signaling that astronomy publications will only continue to rise. So astronomers need to use technology and technological advances such as machine learning to handle the increasing literature, to avoid redoing science and missing key discoveries. Our research team is currently working on a few projects, which we have partnered with the Space Telescope Science Institute on. We started by working on classifying labeled astronomy publications that either use data from Hubble Space Telescope missions or simply just mentioned Hubble Space Telescope missions. So this first project is the paper classification task. Tracking the use of scientific facilities, such as the Hubble Space Telescope, is an important metric for evaluating their scientific value. And the ever-growing literature in science, and specifically in astronomy, has made this task very difficult. As I said before, in astronomy, 16,000 papers per year are published, and this number doubles every 14 years. The Space Telescope Science Institute is currently struggling with this task, and it requires 10 scientists every 2 weeks to step away from their research, their astrophysics work, and focus on this mundane task. However, for now, it has not been possible to easily automate this task by simple keyword searches, as some papers will mention the Hubble Space Telescope but will not use their data. Recent advances in machine learning, and specifically natural language processing, have the power to understand the complex data that are astronomy publications. So our proposed solution is to build an algorithm that automates the identification of Hubble Space Telescope usage in the stream of literature. So the methods that we used are listed here, and here I'm presenting the work on the construction of the algorithm to solve this problem. We began with a collection of 200,000 full-text astronomy papers and narrowed that down to 8,700 labeled papers for the classification task. The next step was to represent the full text in a meaningful machine understandable format. This was done using two techniques, TF-IDF, doc2vec. So TF-IDF is an old technique invented in 1972 by Karen Jones Spark, and that treats a document simply as a collection of words and uses statistics on them. A newer technique invented in 2014 called doc2vec does assign more than just statistical meaning to individual words, such as synonyms, antonyms, and represents the document in a more complex way. And then we ran the machine understandable representation into a few classifiers. These three classifiers being support vector machines, random forests, and multi-layer perceptron. So before we keep going, I wanted to define some vocabulary terms that are often used in natural language processing that I will be using in the next few slides. In NLP, there's a data hierarchy, starting with a single token, which can be a character, subword, or sentence. While a document is a collection of these tokens, as small as a sentence and as large as hundreds of pages of a novel, and then so on, a corpus is a collection of documents, and a corpora is a collection of many corpus. And so tokenization is the process of splitting up text into smaller elements. In this example here, we are splitting this sentence into tokens by word. You can also tokenize by sentence, character, or subword. And then vectorization is a process of representing the tokenized text numerically. There are many different techniques to do this. In this example, we are representing this sentence in one of the simplest ways, using one-hot encoding. And this is representing each word with a 1 or a 0 if it appears in the document. If we use these two sentences as our corpus, the one above and this one, we first have to make a dictionary from all the unique words in the corpus, and each vector will be as long as a dictionary. So here, as you can see, the one-hot encoding representation of they walked home only has 3 ones, as there are only 3 words that appear, and the rest of the zeros are the unique words that appear in the other sentence. And as you can also see, there is no order in where the ones appear, and that is because this is a bag of words model. So no order is taken into account. It's just a bag with the words appearing in random order. So for the classification task, we have to vectorize astronomy publications. TF-IDF is the first technique we researched, and that is a numerical statistic that is intended to reflect how important a word is to a document in a corpus. The TF-IDF value increases proportionally to the number of times a word appears in the document and is offset by the number of documents in the corpus that contain the word. This helps to adjust for the fact that some words appear more frequently in general, words such as if, and, to, and the. The second technique we researched is word embeddings. John Rupert Firth, a British linguist from the 1950s, concisely explains the innovation of word embeddings by saying, "You shall know a word by the company it keeps." Word embeddings are a type of word representation that allows words with similar meaning to have a similar representation. There are various implementations of word embeddings. All of these techniques take into account the order of words. TF-IDF does not take this into account. In these two sentences, word embeddings will look at the context of the sentences and see that pizza and pasta often come after the word restaurant, and will vectorize these words in a similar representation. So then we had to classify these represented texts. So after we represented the full text in a machine understandable format, we passed these documents into 3 different classifiers. And these are algorithms that can be trained to sort data into separate categories. So in our case, the 2 classes, the 2 labels were if it used Hubble data or used the instruments, and if it did not use, if it just simply referenced it. And this included a large fraction of papers that mentioned Hubble data but not used the data in their scientific analysis. So there are several classifiers, and we tested the support vector machine classifier, random forest, and a deep neural network for our research. So after this, we collaborated with Professor Katarina Kahn, an NLP researcher at Colorado University Boulder, and we took a deeper look at the data and at each sentence in which specific keywords appeared. This task showed us that when classifying the two sentences before and after these keywords that I have on the screen, such as HST, the classification accuracy increased to 87%. So as we look at the figure, we can see that the best algorithm combination is TF-IDF with a support vector machine classifier, and that gives us the accuracy of 87%. So we are currently collaborating with the scientists at Space Telescope Science Institute to incorporate the system into their workflow, and we're continuing to explore changes in the current algorithm to ensure that no papers that use Hubble Space Telescope data are misclassified. So here we have a confusion matrix for our most accurate method, which, as I stated before, it was using TF-IDF with a support vector machine classifier. And so a confusion matrix is a summary of prediction results on a classification problem. The number of correct and incorrect predictions are summarized with common values and broken down by each class. This is the key to the confusion matrix. The confusion matrix shows the ways in which your classification model is confused when it makes predictions. So a type 1 error is equivalent to a false positive. So it predicts HST usage, but is actually HST reference. This true label is HST reference. And then a type 2 error is equivalent to a false negative, where it predicts HST reference, but its true label is HST usage. So the type 2 error is higher in our classification, as 19% of the time that HST reference is predicted, its actual label is HST usage, so that it actually used HST data. So to conclude on the classification task, one of the important things to know is that advanced techniques such as a deep neural network or doc2vec, which was the word embeddings, do not always outperform classical techniques. The success of an algorithm highly depends on the data set, and it is important to start with very simple algorithms before increasing the complexity. In addition, it is crucial to add domain knowledge to the problem. Thus, we knew that in astrophysics publications, only a fraction of the paper would describe the observations, and the majority of a single paper contains discussions about other topics. We then decided to split up our long documents and remove unnecessary information and only use our model on the appropriate sections of the paper for an accurate classification. This increased our accuracy from 75% to 87%. Now, something different. So a peer review is a current project we're working on, a peer review task. So peer review has not adequately innovated as technology has advanced, and the dissemination of publications has surged, creating a space for stagnant and biased reviews. The review of proposals for scientific funding takes months due to the sheer number of proposals scientific organizations receive. Specifically, the Hubble Space Telescope receives roughly 1,000 proposals per year, with this number projected to double as the James Webb Space Telescope nears launch. A criticism of peer review is that it is not uncommon for the reviewer matched to a proposal to be from a different field or subfield. Currently, reviewers are matched to proposals through subjective decisions based on whom the peer review committee knows. It is in the subfield of the proposal. It is virtually impossible for peer review committees to unfailingly match the ideal expert reviewer without the application of new technologies. Our technique will expand the choices of possible reviewers to all astronomers in the world, instead of simply relying on who the review committee knows. We will expand on the work done by Kersendorf et al. At ESO at the European Solar Observatory. Their work was done for distributed peer review. However, we will expand the possible reviewer pool outside of just distributed peer review, but to all astronomers in the world. And we're collaborating with Lou Strolger at Space Telescope. So the methods for this project so far in our preliminary results are the construction of an algorithm to identify the expertise for review of proposals submitted to the Hubble Space Telescope. So we began with a collection of 220,000 full-text astronomy papers. The next step was to create a database of all the astronomers worldwide as potential reviewers. This is the step that we are currently at. We are fine-tuning this framework. We are cleaning up the authors based on who is still active, and we have to make sure that we don't confuse authors with the same first and last name as having the same expertise, etc. And then we have to calculate an author knowledge vector, which is a representation of an author's literature. They're all of an author's body of work numerically to then compare to a proposal. So the data set that we are using is called the STORC, the Semantic Scholar Open Research Corpus, short for STORC. So one of the most difficult problems is finding access to all of the full text papers in astronomy. Extracting these papers from archive is the best way to access the publications, as they are open access. Wolfgang Kersendorf, my advisor, has created a pipeline that extracts all these astronomy papers and does some cleaning of tables and random characters. However, the Allen Institute for AI has performed a similar process, but updated this for various fields of study. The STORC dataset is an open source dataset with cleaned full text papers, 220,000 of them being astronomy. And the core of the problem is creating a framework of papers and authors. And the dataset has metadata and full text publications. The next step is calculating a similarity score. And this is done for a proposal and author knowledge vector, and it begins with the representation of the text. Currently, in our initial implementation, we have used TF-IDF to represent the author knowledge vectors of proposals. We first start with an author knowledge vector, which it contains all of the publications for a single author represented in one vector. We then have a proposal, and that is vectorized using the same dictionary as that of the author knowledge vector, so that they will remain constant, remain similar. And so we have a vector representation for a proposal. And then we calculate the similarity score. Currently, we have done that using a dot product, but we are looking at different representation techniques, different similarities techniques. So this is our initial implementation, and we have tested this on a few proposals, one being an old HST proposal written by my advisor, Wolfgang. And after I found the similarity scores for all of the available astronomers, we found that the highest similarity score was an astronomer named Jin Ozaki. And when we looked at the papers that Jin had authored, we found that one of Ozaki's papers consisted of a similar study on the same system that Wolfgang was writing about. So this is an example of how my expertise in natural language processing and Wolfgang's expertise in astronomy helped us verify that the initial implementation of our algorithm is doing what we intended it to do. So here we see the distributions of similarity scores for a random sample of 50 proposals from ESO. We received a data set that consists of 918 proposals recently, and we are going to continue to test on this data set. Many proposals have most of the identified authors having lower similarity scores around 0.4, while a few papers have most similarity scores around 0.6. So we tested another proposal written by Andrew Fullard, a member in our research group, and this proposal is in a niche subfield of astronomy, Wolf-Rayet stars, and the similarity scores for this proposal were much higher, with the highest being 0.81. And this identified author was a collaborator of Andrew's on the proposal. These initial results are promising, as the algorithm is working as intended. However, we plan to extend this work by researching various representation techniques, developing several metrics to validate the identified reviewers, and creating a robust algorithm that can be expanded to other fields of study in the future, using the STORC dataset since we have a large amount of publications to choose from. So just to summarize a few points here. it is important to start with very simple algorithms before increasing to the complexity. TF-IDF and support vector machines are not the most state-of-the-art, but they were the most accurate for our classification task. So you don't always have to start with the most complex. The increasing amount of publications in astronomy are becoming a big data problem, and if we do not implement natural language processing techniques, it will only become harder and harder to understand what work is being done. And NLP will assist astronomers through faster, fairer, and smarter research. And interdisciplinary teams are vital for this research, as I have shown through different examples. And please follow the Deep Thought team on Twitter at DT_42. Thank you very much for listening. I'd be excited to discuss this project further. Please email me at amadovic@msu.edu. Thank you very much.